assim me pediram, mas pode ser em português também.
Não, tem gente que não fala português bastante. So, good afternoon. It's great pleasure to see again Fred Palmeira. For a long time you didn't. I think it's last time I remember your talk. It was like more than 10 years ago.
Something like that.
Yeah, and Marlon Lopez. So they give a presentation. So you probably comment about the memorial.
Yes.
So the lecture is elementary differential topology applied to a problem of partial differential equations, theoretical aspects.
Yes.
So as I understood that we might have the second part in a while. No?
Yes.
Thank you.
Okay. Okay, thank you, Alexei. It's a pleasure to be here again at IMPA. And I'll start. Right. Well, I'll start with a little story. In 1968, that's a long time ago, a group of students from physics department, undergraduate physics students at PUC, moved to mathematics. At PUC, that was a big thing. You know, they finally had 10 students undergraduate in physics, and half of them moved to mathematics. And among these guys that moved to mathematics, there was Dan Marchesin, Paulo Jorge Paes Leme, and myself. Dan started working in PDEs, theoretical aspect, analytical and numerical, and I moved further away to differential topology. But we always kept in contact, we kept being friends. And in 1979, Dan and Paulo came to PUC, to the math department, for a lecture, more of a working session with the topologists from PUC. We are quite a bunch of topologists there. And they wanted to show us an image they have seen, a figure they obtained in some work they had been doing in PDEs related to petroleum things. And they had this figure which was very weird, which was something like that. And we looked at that and nobody really understood what they were saying. And then finally Jovan said, well, you know, I think I've seen this, a figure like that on a recent work of Sotomayor and Gutierrez on principal lines of curvatures of surface. That was it. And 2 years later, Dan and I started, by his initiative, started meeting regularly because he had this idea that there was something to be said with differential topology in CISPDEs. So took us a little while, but I think now we have arrived at some things interesting to show, and it was really interesting, a very good ride ahead in these 40 years. So this is the problem. We start with the partial differential equation, Wt plus Fwx equals 0, which you all probably know much better than me. We have W is in a vector in R2, function of x and t, and f from R2 to R2. We call f and g the components of big F. And when we add these conditions, W of x and 0 equals WL for one side, and WR if x is bigger than 0. This is called a Riemann problem. It seems that this...
What is the definition of WL and LWR?
This is the two constants. Two constant states. You give these two constant numbers. This is initial condition, sort of equation. It seems that this is called the Riemann problem because Riemann, studying propagation of gases in tubes, arrived at this modulus, this equation. So it's been called the Riemann problem ever since. And that's all I know Okay. And there are discontinuities that the fact that if f and g are nonlinear, this produces discontinuities in the solutions. Okay? We are interested in three kinds of solutions. One, which is called rarefactions, are solutions of this type, where w is a function of one variable, lambda, where lambda is x over t, and then you plug it there in these partial differential equations. So it's differentiating. You differentiate with respect to lambda, and then differentiate lambda with respect to t, and same thing here. And finally, you get this equation there, and you divide by t, and you rearrange it, and you find this nice equation, which is just, you look at that, and you see that lambda is an eigenvalue, and w prime is a corresponding eigenvector. So you are looking at line fields of eigenvectors of the f of w. Fala, Jorge.
How the diffusion equation a special case of the equation you're considering?
I don't know. I don't know.
Any other classical equation?
I don't know.
The diffusion equation is of parabolic type, yes, and these are like more hyperbolic problems.
Yeah, this is the conservation law.
It's a constant.
Okay? So those are called rarefactions. And second type of solution we are interested are the one called shocks, which are just W1 for x smaller than for some sigma smaller than sigma t, and W2 another constant for x bigger than sigma t. And then you need that W1, W2, and sigma satisfies this equation. This is called Rankine-Gounod equality. Okay? And if you fix W1 and the set of W2s for which there exists sigma, it's called shock curve. Okay? So this is terminology. And there is a third type of solution, which are called composites, which are kind of put together mixed shocks and rarefactions. Okay. So this is the three types of solutions that we are interested. And then we'll define later on what will be composite curves. Okay. So we started the first relevant case, which is studied by Schaefer and Scher in this paper, is when you have df of 0, 0 is 0, and for outside of the origin, you have df of uv has two linearly independent eigenvectors. 0, 0 is called an umbilic point, and then Schaefer and Scher, they showed that in this situation, it is sufficient to consider, well, if you have it is sufficient if you have a second degree polynomial, f, let's say, yes, no, if you start with a second degree polynomial, f and g, second degree polynomials, you need only to consider the case where fg is a gradient of some third degree polynomial h. Okay? And that they describe the curve. There in that paper they relate the rarefactions curves with the lines of principal curvature of the graph of the surface given by z equals h of uv. Okay? And the second case, what we did was add linear terms to f and g so that fg is no longer a gradient. So you start with this f and g, yeah, and now you add linear terms, but in such a way that you don't get a gradient anymore. So what happens is that the umbilic points will explode into an elliptic region, which actually, since everything is second degree, the elliptic region will be really the interior of an ellipse. Okay? And now, so to study that, we introduced the notion of wave manifold, and this led to construction of solutions of the Riemann problem. Wait.
So when you say elliptic region, there are two things. First, it's elliptic region because of the change of the eigenvalues, and also So
Yes.
it comes in the ellipse
Yes,
plane.
yes, yes.
Ellipse comes in.
Comes to two ways, yeah. Yes.
So it should be a V ellipse.
But, like the umbilical point is a point only if the flux is the gradient.
Uh,
I mean, if it's not
Well,
gradient,
if you have no, if you have this you have f and g polynomials of degree 2, with this condition that you have this linear independent eigenvectors everywhere and 0 at the origin, then you can just change of it's enough to consider the case of a gradient, and that leads to the lines of curvature of the surface. Okay, that's related to that. So now we don't have any more polynomials, any more gradients. And we are going to start, I'm going to start to show you. So this is the f and g that will be working with. It's a little different. Notice that, yeah, there you have two parameters, a and b. That's age of uv, it's actually to be a general polynomial of degree 3. There is a v3 missing, and there are some coefficients there missing. uv2 is coefficient 1, and v3 has coefficient 0. This is just appropriate change of coordinates. You can reduce it to this form. Okay? And what we did was we switched a little bit the switch variables so that you have these constants b1 and b2. And you'll see in a little while why this choice of b1 and b2, plus the linear terms. And so that it's no longer a gradient, you have the condition will be that A2 is different from A3. Okay? It's an equivalent form. So now we'll try to get rarefaction solutions. You have there, you just write df equals w prime equals lambda w prime. So you write the eigenvector as du dv, and you just write the two equations and eliminate lambda, and you get this nice differential equation. You have either this one and this one. That's the usual thing you do in differential equations when you want to consider also vertical directions. So you switch to du dv. Okay? And one thing you can do that is just to, this is not the usual du dv equals f of uv. You have du dv squared. This is what's called sometimes multiform differential equation. This is something people have studied. And this second degree, it's easy. You just solve the second degree equation in dv du and get dv du equals something. But then there is square root there. It's annoying. So what we did was to go back to Lagrange and use what's called the Lagrange method. You write z equals dv du, replace dv du by big Z, and now you look at this, you have this surface in variables u, v, z, and the differential equation becomes z du minus dv equals 0. So this is a differential form that gives a differential equation in this surface. Okay? And this turns out to be easy to solve. Why is it easy? Because you see, there. Well, let's go see this equation. And you look at there, you see that first, if you fix z, you have a ruled surface. You have a line in uv. For every z, is a line in uv. So you can, when you use, and it's easy to solve that in u or solve that in v. If you solve that in v and put it back in the differential equation, actually you have a differential equation, an ordinary differential equation in u and z, or in v and z, which is linear, because everything is linear here in uv. So it's easy to solve. And you can obtain explicitly the formulas for this equation. So you solve that, you project from the surface to the UV plane, and there you get it. You see that since if you fix u and v, you have an equation in z square. So you have 2 points. You have 2 points in this surface. You get 2 points for each uv, 2 points surface. So you project, then you have you have the two line fields there. You have one family and the other family. Okay? And if you go back here to lambda, that we had eliminated, where is it? There. You see that if you divide by du, you have lambda equals fu plus fv dv du, so fu plus fvz. So you can look at lambda as a function in the surface. Okay? And if you look at it as a function in the surface, you can look for critical points of this function restricted to trajectories of differential equation on the surface. Okay? And this set of critical points is called inflection locus. And that is something that at the time that Dan told me, look at that, that's something important. We are interested in knowing what is this curve. So we did that. So the surface, this is a picture of the surface. The lines there are there just to show. This was done by hand, and it's 1980. So the lines is just to show that you are one side and the other side and go back to the side. So C is actually a ribbon twisted twice. And when you glue Z infinity with Z minus infinity, you get not a Möbius band, you get a cylinder because it has two twists. Okay? And this picture is where you see on the left side, you see the ribbon untwisted. And on a simple case, you had only one singularity. There are three different cases. You can have one singularity, which is a saddle, three singularities, which are one node and two saddles, and three saddles. So this is just fixed one case, one simple case. And there you have the ribbon untwisted, and there you have the result, the projection, when you project in the plane. So you see there's this one set of curves and the other set of curves.
On the picture of the ribbon, it seems that there are pieces on one side which are parallel, the other ones are parallel, but in between.
No, this was just an effect to show that there are different sides.
Okay.
These lines have no meaning, no meaning in the.
The line from the rolling is.
Yeah, these lines have no meaning in the differential equation. Okay? Actually, you'd have here, you'd see, this would be the lines Z constant, which you don't see Z because on the other side. That's all this was the artist's conception to show the, because at the time we had no computer, it was done by hand, by a draftsman, a draftswoman. Foi a Luciana, com a mulher do Tom do Carro, lembra?
Photographer.
Luciana, photographer, yeah.
Whittaker.
Luciana Whittaker, yeah, she did the pictures. Okay, so this is the other case. This different cases depending on the values of B1 and B2. So this is a case with two saddles. There's one node here and two saddles there. When you project, you get this picture. And the three saddle case where you have these three pictures, these other pictures there. The singularities, when projected, they are these points where the lines are tangent. The line fields become tangent to this. Let me see a little bit of what is that circle. That's that circle there in the middle. Yeah. See, you look at the equation there. It's a second degree polynomial. When you try to solve the VDU, you have the discriminant. So it will be the VDU equals something plus or minus square root of that thing there. And if it's negative, it's a region where there are no solutions. That's that ellipse that you saw there. That's that elliptic region. So here there are no rarefaction curves. So this is what's called a hyperbolic region where you have really two rarefaction curves. This curves. So this line here is the one that projects into this circle. So this is one side. It divides the ribbon in two parts. So this is one side of the ribbon and the other side of the ribbon, and they go. One side goes to one line field, and the other side goes to the other line field.
Yeah, when you said in that region there's no solutions,
No solution.
Solutions that blow up because they're elliptic. I mean,
There are no rarefaction solutions.
oh, no rarefaction.
No rarefaction, yes, because you have to, this is a differential equation you want to
So you have
solve.
the lambda that's specialized for rarefaction.
So this differential equation is not defined in the whole plane. It's defined only outside of the
The
ellipse.
question is different. So from the original PDEs, before doing this self-similar blah, 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 in the elliptic region, is the solution of the original problem, whatever, unstable because the eigenvalues are not real or not?
Isso aí, Dan, pergunta para você. Dan.
Should be imposed, right? The solution should grow, right?
I have a stupid question.
I think here is still the question of existence of solution. So I don't know if they exist.
Okay.
If you have a point in the
Inside.
equation. That's the question.
Yeah, because I used to think of the elliptic region being a region where the eigenvalues are not real anymore, which means hyperbolic. And since they are complex, solutions could grow, right? Could be unstable. But I don't know if that's the case.
Usually, so high frequency mode, they
Explode very high frequency.
Is the circle the warp of the signal?
Yeah.
I
Okay.
only want to not know what is rarefaction.
Excuse me?
I'm supposed to know what is rarefaction.
Rarefaction are just these curves. These curves are called these solutions are called rarefaction curves. These curves that you obtain by integrating these line fields of eigenvectors. Okay?
Nothing gets rarefied.
No,
It's just a name.
it's just a name. As far as I know, it's just a name.
If you collapse the circle, you have the initial.
Yeah.
three-
Yeah.
Okay.
Yeah. Okay. So, as I was saying, in the exterior of the ellipse, there are two linear independents. So this is called an hyperbolic region, and the ellipse is common boundary of the hyperbolic and elliptic regions. It's called coincidence curve. Okay? So it's a name, and in the UV plane, rarefaction. Yes, when you are on top of the ellipse, right on the ellipse, you have the two. Here you see they are independent, and when you arrive here, they become dependent. The two become one. That's double root of the differential equation, and here complex root.
And you can have any type of ellipse. It can be almost a circle,
The ellipse will be it's something you obtain from the coefficients.
and you can vary.
Yeah, it depends on the B1 and B2. Okay? Okay, so after we did this work on rarefactions, the idea was we want to study shocks now, which are given by, we want to study the shock curves. Okay? So you have this, recall that you have this expression, U prime, V prime. So this is a shock curve in the plane. Okay? Set of U prime, V prime such that there exists sigma such that for a given UV, for a given UV, the set of all U prime, V primes is the shock curve defined by UV. When you vary UV, you have all these curves very mixed up in the plane. So the idea was to copy what we did for our rarefactions. Just go to some space. That is, rarefactions, you have two line fields like that, and you went to this surface where they are nicely separated. And so now the idea is to try to do the same thing with this discontinuous solution. And this was done by a blow-up procedure, which is actually here is just, remember that there you had Z was dV over dy. So this is a kind of discrete version of that. See? Z will be difference V minus V prime over U minus U prime. It would be dV dy if you collapse, if you make U prime, V prime tend to UV. And you call X, big X, the difference U minus U prime. You define these new variables X, Y, U, V. And the Rankine-Hugoniot equation becomes, again, two equations, and you eliminate sigma, and you get this one here, which defines a surface. If you call G these functions, G is just put everything to the same side, okay? and you see that g equals 0 and y equals zx, this will define a three-dimensional manifold. Now you have 5 variables, u, v, x, y, z, okay? And 2 equations. So it's a three-dimensional manifold in a 5-dimensional space, which actually is not really R5 because z is a direction. So it's R4 times S1. Z goes to get together there in the circle. Actually, it should be projective space of dimension 1, which is just a circle. So we're not big. And notice that this is quite similar to the surface that we found before. This surface C that we found before. And you see that for every Z fixed, again, it looks like a rolled surface. You have planes. For Z fixed, you have planes u, v, x, y. So you see linear equation u, v, x, y. Actually only in uv. And these planes keep moving, can keep moving like that, and then they glue together, and you can compute that and see they glue together in a non-orientable way. So actually, it's not R3, it's a Möbius band times R. It's not a cylinder times R, it's a Möbius band times R. So this is the wave manifold. And in the wave manifold, what are shock curves? Shock curves are uv constant. uv constant is a set of u prime v prime. Little u little v constant can be written as du equals 0, dv equals 0. And now you can check that dg dy minus dx, which is just these two equations represents given by the manifold, and du, which in these new variables is just d big U plus dx over 2. These are linearly independent. So being linearly independent, it means that for each u0 fixed, this surface, this is a surface of dimension 2, which as u0 varies, you have a foliation in the wave manifold. So this is very nice because you had to study a curve family in a three-dimensional environment. So now you foliate it by two-dimensional surface, and it's a more tractable problem, which is level curves of this function v on each leaf mu0. Okay? Also notice that if you intersect M, this manifold, with the plane x equals 0, you get a surface which is exactly the same equation as before. It's the same surface. You can identify that with the surface C, which is called the characteristic surface. And the sigma function, remember that we eliminated sigma here. Where is it? Yes. We eliminated sigma to get the equation. Just how we eliminated, same way we eliminated lambda. Okay? And this sigma restricted to C just coincides with the function lambda we had before. So it all fits together nicely. Okay? And in the same way we define Lagrange prime curves, you could define what we call Lagrange prime curves, which is just instead of fixing uv, you fix the other one, u prime, v prime. So you have the same thing there. And again, we have these two surfaces which we can define. You can look at the function sigma. Erramos essa, hein, Marlon? We missed this one. This should be sigma instead of lambda. Yeah. We missed that one. Yeah. We were correcting the slides even 10 minutes ago, and we still missed one. That's the way it goes. And so you have the sonic surface, called sonic surface a set of critical points of sigma restricted to Lagrange curves, and called sonic prime the set of critical points of sigma restricted to Lagrange prime curves. Okay? So this is what a typical picture of a Lagrange curve on one of these leaves looks like. See? Typically you have one or three you have singularities which corresponds to the same values of z that gives you singularities of the rarefaction fields. So this is a picture in the case where you had 3 singularities for the rarefaction, so you have 3 singularities for the shocks.
Sorry, Fred, I think
Right.
I got distracted. Why some of these critical points are called sonic points?
That was the name it was given to me. Por que isso é sônica?
Coincidence of shock speed with characteristic speed.
Sorry?
Coincidence
Our shock speed with the same characteristics.
Yeah.
Okay.
Okay.
Would that be like a critical, I mean, a short, I don't know, like a fastest possible shock or not? No.
Keep in mind.
Pretty much, right? That's sonic, right? But like, I don't know. I'm
It's kind
trying
of
to guess.
singular situation. Usually it's in between.
Usually that's right. Usually it's between. So
Yeah,
if it
but-
coincides, it looks like a speeded up shock, right? Is that maybe why it's called sonic? Okay, thank you.
Okay.
Usually you don't have it.
Okay.
So this is a typical leaf on a case of 3 singularities. Okay? And notice, although in for rarefactions, 3 singularities can be one center and 2 saddles or 3 saddles, here it's just the same. You always have this saddle type of singularities, singular points. Okay? And the singularities here, when you move these singular points, they describe a straight line. The straight lines which are called secondary bifurcation set. Okay? And the other separatrix, which is this curve here, so the singularity generates a straight line. This straight line separatrix will generate a plane. It's a plane z constant. And you have also these curves here generate a surface which we call a saturation of secondary bifurcation, which is just if you take this line that is coming like that, and you take all the Hugoniot curves from this line, it will define a surface which will have some importance in what we'll see later for the solution of the Riemann problem. So it's called the second separatrix of secondary bifurcation surface. So we did a lot more of constructions with the wave manifold, and these are some facts which are in this paper I wrote with Cesar Ashkenazi. It appeared from 2002. And these are the facts that we will need. Fact 1, C, as I said before, is topologically a cylinder because it had 2 twists in the ribbon. So EC is that curve that bounds downstairs in the UV plane. It was the boundary of the ellipse, E. When you move to C, there's no ellipse anymore. It's just a simple closed curve which does not bound the disk in C. So if you think at C as a cylinder, let's say C is a cylinder, it's just a curve like that. Okay? Not something like that which bounds a little disk. Something that goes around the cylinder. And those separates in 2 components. We call them CS and CFs, for slow and fast. Why it's CS and CF? Because the speed of the lambda or sigma in CS is always smaller than the one in CF. Okay? And fact 3 is that if you take a Hugoniot curve, either it intersects C transversely in 2 points. One will be in CS and the other one will be in CF, or it intersects 2 points, or it doesn't intersect at all. Took too much out. It should be said, it should be written here, the notification for USS, or it doesn't intersect at all, or it intersects, it is tangent to C along EC. Okay? So there are these 3 possibilities. Either it is coming in here and outside, in CS, outside in CF, or it just goes like that, or it's tangent if it's tangent along this curve C. Okay. So Son and sonic prime are actually topological Möbius bands. Okay. Remember, it's everything is linear in U, V, X, and Z. So again, you have Z, and you fix Z, and you have this plane. For the sonic surface, you have this line going twisting, and when you glue, it's non-orientable. So you see it's a Möbius band. This is all tedious, but straightforward computation. And also Son and sonic prime, they intersect in the inflection locus, and also they may intersect in two straight lines, each of which intersects transversally C at a point of inflection locus. This is what's called the double sonic locus. We'll see pictures of that a little later. And now this is what was allowed us to define the composite curves. The fact that generically a Hugoniot curve through a point U, age of U is a Hugoniot curve, it intersects on primes in 0, 2, or 4 points. If it intersects in 2 points, sigma has the same value in these 2 points as the value of sigma either in US or either in UF. Because you see, remember that the intersection, as we said before, it's 2 points. It's one in CS and one in CF. And the value of sigma at the point in sonic prime cannot be anything different from those two values. And at the 2 points, either the 2 points have the same value in CS or the 2 points have the same value CF. Okay. So in the first case, when you go down to CS, you define what's called the slow sonic prime, and this in second case, a fast sonic prime. If the intersection have 4 points, then they go by pairs. The values of sigma go by pairs. You won't have 3 and 1, or 4, or the 4 values in the same point. It's 2 in one side, 2 in the other side. So now we can define what would be the composite curves. You have this map. This allows us to define a map. So you start with a point in sonic prime. Take the Hugoniot curve. It will intersect in 2 points, US and UF. Compute the value of the speed in U. So the value of the speed here in U is either the value here or the value here. So psi of U will be US if sigma U is sigma US, or UF if sigma U is sigma. So you choose, you define this projection from the sonic prime to the characteristic by choosing. You have 2 points. Which point you choose? You choose the one that has the same value of the speed. Okay. Now you can pull back with this map psi. You pull back the differential equation from C to sonic prime, and this will give you what's called the composite curves. Okay? And these are related to the composite solutions as we wrote before. Okay? And actually, for each singularity of the rarefaction, well, this psi is kind of a double cover of C, of its image. Its image is not the whole C. And each singularity of the rarefaction will generate 2 singularities of the composites, which are of the same type. And plus, you have also 2 extra singularities, which are just centers, which are obtained by the intersection of what we call double sonic locus. Remember that? These two, I said there were 2 vertical lines, 2 straight lines, and when they intersect C, they give you centers. This was most of practically all this stuff is in my paper with Cesar, except for this part of the characterization of these extra singularities, which you can find in Basto Gonçalves and Helena Reyes' paper, which is a very nice paper. It's comprehensive with all we had done before in shocks and rarefactions, with very beautiful pictures. This was 205. Okay. Now, to solve Riemann problems, you really need something else. You need what is called lax admissibility conditions. And these conditions can be translated in this topological setting the following way. You take an arc of a Eugonio curve, okay, in the wave manifold. This arc of Eugonio curve will be said to be admissible if it satisfies these three conditions. Okay. First condition, the arc is oriented in the direction of decreasing sigma. You want arc decreasing sigma. Second condition is that for every point in the arc, sigma is smaller than the value of sigma in US. So remember that I'm supposing that the arc intersects C. So you have these 2 points US and US. So you can see that one way of getting one way of getting the arc that satisfies 1 and 2 is just you start in US and keep moving in the directions as sigma decreases. And you move until you arrive at the sonic. That's where sigma changes its growth. Remember that sonic surface is a set of points where sigma is critical along the Eugonio curve. Okay? And here we are supposing, so generically it's transversal. So if you keep moving until either you go all the way to infinity, or you stop at sigma because sigma was decreasing, and that's a sonic. When you pass a sonic, sigma will change, will be increasing. So you violate condition 1. So admissible arcs would be, up to now, would be arcs that either start in CS and go down until you find sonic or go all the way to infinity, or they could start also in sigma in the sonic prime, where value of sigma is the same as the value of US, and you do the same thing and you stop when you arrive at sonic, or you go all the way to infinity. So this, when you start at sigma, when you start in CS, it's called a local arc. When you start in sonic prime, it's called a non-local arc. And there is this third condition also that you need to satisfy, which you take any point U in the arc, you have to take the Eugonio prime curve, and you check where it hits CS and CF, and you need to satisfy this condition here. And this will limitate the arc. So not all arcs. So if you take any arc that satisfies 1 and 2, not all of them will satisfy condition 3. Okay? You disregard some of those. So it's an interesting thing to characterize what are sonic prime S and sonic prime F, and also from a topological point of view, if you look at these conditions, you said, well, I would like to know, given a point in the wave manifold, I would like to know if that point belongs to an admissible arc, a local admissible arc, a non-local admissible arc, or a non-admissible arc. It should be, all these conditions are continuous, so you should divide, the wave manifold should be divided into blocks. In each block of these are all the same type. And this was done in a simpler case, which was, we had these two parameters, B1 and B2. This simple case, which corresponds to the case where we have only one singularity in the rarefaction or in the shock, which was called case 4 in this Schaefer-Scherer classification. Okay? And we are still working to get it all for all other cases. And this was all done to get these characterizations and all this stuff with some new coordinates, to a new coordinate system. So I'm mentioning it because that's where we will see we obtain pictures. And these are the new coordinates. These are not chosen by chance. The idea was to look at the ribbon, and then in the ribbon you have that coincidence curve there, and then you you choose coordinates like that. You go along the coincidence curve, and then you move horizontally in the z constant in the direction. You move away in the direction which is orthogonal to the characteristic curve, orthogonal in C to the coincidence curve. That's what. And this gives you a nice coordinate system that is valid for all the ribbon, in all C of the ribbon. So this allowed us to get some nicer pictures and to find these subdivisions. Now that was all done in this new surface. So in these coordinates, just say that C becomes the plane. So it's YT and Z. And this coordinate C just becomes a plane, so it simplifies a lot of computations. The coincidence curve is just a line t equals 0, tau equals 0. So one CS will be one side of this line, and the x of the other side. And there are formulas for all surfaces, everything that is involved. And now I'll show you a couple of pictures, and then Marlon will tell you more about how we use that how can you use that to solve Riemann problem. So this picture is in the new coordinates. You have there the sonic surface, which is this blue, kind of blue saddle, see? And you have this is a characteristic surface. It's, as I said, it's just a plane. So one side is CS, the other is CF. And the green surface is the sonic. The sonic is just a symmetric, the reflection of the blue. So you have the blue saddle where you can really sit there and nice, and then you reflect it. And then you have these two saddles. You have these two saddles, there becomes a hole in the middle. See? There's a hole there in the middle. And you can fill that hole. Now, this new surface is the saturated of the coincidence curve. So you take the coincidence curve, take all you go on your curves through points in the coincidence curve. And this generates this surface, which is kind of cylinder, and it is tangent. It is tangent here to, this is just a defect of the graphic computation. It is really tangent to the blue surface. Okay? And you can have also the symmetric thing, which is the saturated of the coincidence curve by Hugonot prime curves, and it will be tangent to the sonic surface. So these are some of the elements that we will use. It will be needed to solve Riemann problems in this context. And here you see just the blue surface, just the sonic prime surface, and the saturated of the coincidence curve. Okay? Coincidence curve will be right here. And you see the yellow is the tangency curve between the blue and the magenta. And you have this straight line here, this red line. And the fact is that the yellow and the red are separate sonic prime in sonic prime S and sonic prime F. Okay? So here you'd be sonic prime F, sonic prime F. It would be something, you had just something locally, just a saddle. Okay? So this would be red, let's say yellow. And so you had sonic prime S, sonic prime F, sonic prime S, sonic prime F. And when you go all the way to infinity, to Z infinity, it glues, but it glues with a twist. So F, sonic is fast, glues with fast, and S glues with S. So it's nice. And the green lines here are the double sonic locus. And it's important also because in the sonic prime, the region between these lines correspond to the points that satisfy the third condition in the admissibility conditions. Okay? So if a curve hits a point here, it will not satisfy the third condition of admissibility. It need to be here inside these two green lines. Okay, ups. So that's all I had to say about this topological settings for for the wave manifold, and now Marlon will tell you a little bit about how can we use that to solve Riemann problems, which will be to talk about that more extensively in a later date.
Well, thank you very much. Now I'm gonna try to put at least give a perspective of how this topological tools that were developed by Professor Dan and Professor Fred and collaborators during the years. First of all, what we want to do is to use this whole topological equipment, if you want to put it in some way, in order to solve the Riemann problem. Usually what we have is presentation. We have presentations on state space. Yes, only quadratic, yeah, yes. So in this case, what we have this presentation here is the slow wave curve, which is basically presented by this curve here in blue. And we want to use this all this equipment in order to represent everything that this has in the wave manifold. Here we have in this this would be the elliptic region, which would be mapped in, which is actually mapped in this one here. It's kind of a representation of it. And we're going to use, in order to do this, we're going to try to use the main basic curves, which will be the Hugoniot curve, which would be this one here. If you fix a point here in this characteristic plane, we're going to have another point that touches in both sides. So we have all the connection between the two characteristic planes, the fast, the slow characteristic plane and the fast according to the speeds. Then we're going to use also the Hugoniot curves, which are these curves. If we put them both together, we know it's a reflection of them. So we have a reflection. That's why in this figure here, we have these two presentations as this. So how do we use this? Well, first, we're going to have the representation of this low curve in state space. All of these will be represented in a three-dimensional setup. So we have the slow shock curve. We have a slow rarefaction curve starting from this point UL. And then we have a composite curve that actually goes up here in this representation. We're going to be using the Hugoniot curves and the Hugoniot prime curves in order to represent this solution. And specifically for this ones, we're going to create saturations. Basically, we're going to take Hugoniot prime curves, and in order to create this kind of surfaces. So if we have this kind of surfaces, what we have is we have a characterization or a representation of all the points that connect the characteristic planes from both sides. So if you see from this side, from the slow side, we connect to the other side, as we saw on the Hugoniot representations. And then every one of the curves will have a surface. Specifically, in this specific case, we have all the saturations, but there are points here that they will not have a composite curve. But in order to represent this, we took a point that actually has this representation in 3 dimensions. And we're going to try to do the connection with a fast curve. Fast wave curve. So what we have here is the representation that we're basically finding in state space. So we have all these connections, and we see that there's a point that they intersect, and then it continues here. But in our setup, we can see that we have a different, more richer structure that gives us more information of how they intersect. So we can see at this point here, there's an intersection, and visually we can actually determine how to, or where in order to get the intersection, and we can determine if there's a solution for this specific problem. All of these, it took almost 40 years in order to get this whole representation. And in a later presentation, I'm going to present the whole all the algorithm that I actually was created in order to present all of these, and we're going to try to do some applications for real problems, and this at this moment, this is the last thing that we have presented in this work. And basically, I mean, we have some. Yes.
So once again, so you pick some point, yes?
Yes.
You have like a slow wave curve.
Yes.
Curve.
Yes.
And here you represent some surface. Is it a collection of wave curves at different points? Or
Yes.
what is
No, it's 1 point. No, actually, what we have is this. We have this slow wave curve, right? So what we have here is that we take the saturations, or basically we take the Huygens prime curves, these curves that are in red here, and what we do is that every single point from here, we take a Huygens prime curve passing from here that actually connects the other side. So when we present, for example, the purple one, we have a Huygens curve that goes from this side through all of the points from this specific curve, and we do the same thing for all the curves that actually are created starting from this point that we choose here. So this will be the representation of the UV point that is actually taken from the state space, projected into the wave manifold, and then we create this representation in 3 dimensions, and then we do the saturation surfaces. Why do we want to do this? Because since we want to have this connection here, no, I'm sorry, this connection that we have in the state space, in order to connect them, we do these surfaces, and then for the fast wave curve, we only do the intersection of the fast wave curve, which is this red one here, and then we see that there's a connection point from there.
So,
Yes.
so these curves are like a trajectory, parameter-dependent trajectory in the space. I mean, what does this curve mean? How do we evolve? When we do a curve that connects from here to here,
Yes.
to me it sounds like we're propagating some parameter space. So how do you construct these curves?
As far as I understand, it's like a collection of all points.
Yes.
So you pick one point, for example, left,
Mhm.
and you take all points to which you can go through some slow family. So it's not a trajectory, yes, but it is like all points to which you can go
From one side?
from one point from the left.
Yeah.
And then you do the same. You have a Riemann problem, yes. So it's left point and right point.
Yes.
And then you take right point and draw a fast wave curve, yes. So it's a collection of all points from which you can go to your right state.
So the curve is this collection of
It's
points.
a collection of points, yeah. So it's not a trajectory of sorry, it's a collection of all points such that you can go. And then you intersect these two, right? These two lines, curves. And if there exists one intersection point, that means that you have found some intermediate state, yes, and you can go from the left state to the intermediate state and then to the right. At least this is how I interpret it.
Yeah.
It means that this curve is parameterizing.
I'm sorry.
This means that this curve can be used as a parameter.
I'm sorry. I don't understand the question.
I mean, from what I understand,
Yes.
there is a way to, for each point along this curve, you will have your solution, one of your curve
Mhm.
joining. And so, and this set of solution joining seems to be parameterized by,
By the coefficients of the yeah. So we're gonna have obviously it's gonna be connected by the parameters of the flux, and we have all the representations of this. All of these curves are gonna be represented by those parameters. So whenever we do this connection, what we're basically representing would be this, but in a 3-dimensional setting.
Okay, so Charles' question goes a little bit along the lines of what I was thinking. So you change this collection of, do you change a parameter as you go from point to point, as you were saying?
We're basically what we're doing is that we're joining all the set of points that are admissible for that specific construction. I mean, first we taking into account the velocity, which would makes it.
When you, like, what changes when you go from one point to the other, as Julia was explaining to you?
No, what?
Charles was asking about parameters.
So, for example, the blue curve, yes, it has different parts. For example, it has
Yeah.
part which is a solid curve, yes.
Yes.
This corresponds to smooth solutions, which were reflection waves, yes. So there you change the characteristic spin, yes. And there is this parameterization, yes.
So you're changing some, so that's a
Yes,
little bit,
but
that's a
it's
little
only
bit
for
what I
smooth
meant, like
solutions.
evolving a according to parameter, no?
Yeah, but it's only on the solid curve. You can think of it, yes, that it is a rarefaction curve, and yes, there is this natural parameter, the characteristic speed,
Sliding around.
sliding around.
Oh, okay.
But if you take a point on the shock curve, yes, on the
Okay.
dashed line, yes, and take any point there, then the solution that corresponds to these 2 points is just discontinuity, yes. So this curve is parameterized by the speed, speed of this shock solution, yes. So like the parameter of this curve is the speed of this shock solution.
That comes out as
There, yeah. So in this sense, it is parameterized by.
By some, that's what I was thinking about.
Okay.
Something sliding along the curve. That's what I mean. Okay.
And what about the other type of dots? The dots.
The other type of dots is when you have, like, you can combine the solution being a discontinuity and a smooth part. So you have both of them, or maybe more than two, and then you draw these dots.
Yeah, and in this situation, what we have is that we can find solutions in this way, but we can determine in a different way all the interaction of all the curves using this three-dimensional representation. I have here, let's see if we have some time. Probably we might have not, I mean, because we're already past the time for this. But, well, it just froze up. Anyway, in a later presentation, what I'm going to do is that I'm going to specify all the whole algorithm in order to have this presentation done, because it took us some time in order to just represent all of these surfaces in order to have all this representation that we have here, and in order to understand and make the interpretation of what we have as a solution for the Riemann problem. And actually what we find here is that we're going to have an interaction with all the curves, and we can determine the intermediate state, as Julia said. Yes?
You thought about trying to use a 3D printer?
Well, we have just managed to do this week. So yeah, we might choose to do some printing later on. That will be an interesting thing as well. I don't know. I don't know for this thing. Well, up to this point, this is what we have, and we already have the algorithm, and we're extending this to a bigger presentation. This was actually presented in one of our papers that we submitted recently, and we're expanding and extending every surface in different forms, and try to make the whole classification of the Schaefer-Scherr classification, which actually for cases, but it's going to take some time. Well, I guess we already have finished our time, right? And I guess, well, that's it. And everybody, thank you very much for the presentation for this part.